weeks and then we get a break.
How many weeks?
Don't we get a Thanksgiving break?
2, 3?
3 weeks till the week off.
Tuesday or the Thursday. That was a Thursday. The week after.
Okay, so good morning, everyone. So you're going to have a break before the Thanksgiving break. I have a conference on the week. I'm going to travel on Sunday, November 11th. I'll be out for almost the entire week. So we won't be having lecture on Monday and Wednesday of that week. I'll be back on Thursday. So we're going to have lecture on Friday. So Monday and Wednesday, most probably, what we're going to do is we're going to have the midterm exam on either those, one of those 2 days, Monday or Wednesday, okay? So that we don't miss a lot of lectures, okay? So we're going to have the midterm exam on Monday, November 12th, or Wednesday, November 14th, whatever you prefer. I'm going to have someone proctor the exam, okay? I won't be here. So you're going to have a break before the Thanksgiving break. Just break from me.
So you want to prep either Tuesday or Thursday?
Yeah, I will do the same. I will have the midterm exam on either Thursday or, yeah. Okay, so for the what we did last time, okay, some of you was not here, so I'm going to go through the slides here. We didn't go through the slides. We used the, written hand notes, okay? But anyway, for the, when you have a shear force, the shear force will result in diagonal tension, okay? The diagonal tension is related to the magnitude of the shear stress and the normal force due to the bending moment. Close to the support, the normal stresses is equal to 0 because the moment is small, and the shear force is maximum. So this is, the transformation of the stresses at one element like this. So this is what we get here. The tensile stresses, here you have maximum moment, and the shear is almost 0. So the tensile stresses is only due to the bending moment. And then here, as you go this way, the shear is going to increase. So the tensile, there will be tensile stresses will get by 45 degrees as we show here. Okay. So as you see here, there will be those cracks, which we call flexural shear cracks. Okay. It's going to be oriented by 45 degrees. Okay. So we have those cracks over here. You see, this one is more clear. Okay. Those are flexural shear cracks, okay, due to this diagonal tension due to the applied shear, okay. So the shear would result in web shear crack, okay. So those cracks, okay, the flexural shear cracks, it initiates from the top of the flexural crack, and web shear cracks forms independently. So there are two forms of cracks here. You would have a crack that only forms on the web, that would be somewhere over here due to the shear, but the most popular ones are flexural shear cracks. It starts due to the tensile stresses due to the bending moment, and then it continues, the crack continues up due to the effect of the shear, okay? So when you have this flexural shear crack, okay, formed like this, it will be resisted by the Dowling effect on the tensile bars over here, the aggregate interlock between the two parts here, and the shear strength of the concrete compression. All those three effects, if you add them together, okay, we call this the shear strength, okay, the shear strength of the concrete, VC, okay. How much is VC? That can be provided by the concrete on that section. It's given by this table and this equation, okay? Both of them gives you the same value, but the same VC, but one of them is more conservative. So this equation 22.5.51. It's less conservative, so it's going to give you a smaller value. And this equation will give you a larger value, but you need to know how much is V ultimate and M ultimate in a given section. Okay? If you have in the beam has some axial compression force or axial tensile force, you don't use this value for VC. You don't use those values. You have to use any of those values. So if it's under compression, you have to use this equation where NU is the compressive force. If it's under tension, then you have to use this equation where NU is the tensile force on the section. Okay, so that gives you the strength of the concrete. Okay, the nominal strength of the concrete to resist the shear force. Okay, it's function of FC prime, B web, and D. Okay, so the dimensions of the section. It's not a function. This conservative equation, okay, is not a function of the amount of steel that you have. This equation is a function of the amount of the steel that you have, rho. Okay. So now, if your applied shear force is larger than the strength that the concrete can provide, then you need to supplement this or reinforce your section with steel reinforcement. Okay. So the web shear reinforcement, you have those three types. Okay. Stirrups or inclined stirrups or bent up bars. Here are some figures for those. So those are bent up bars here. You have bent up bars. You bend up the lower steel into top steel or negative steel. Okay, and while it's bent, it's over here. This bent bar over here, bent up bar, will resist some tensile force. Okay, or you can have vertical stirrups to resist the shear along that track, or inclined stirrups, okay, like to resist the shear. You can have your stirrups as just one branch of a stirrup. If your wet, the beam width is so small, you can just provide one branch. Here you're providing two branches, okay? Here you're providing four branches, okay? You can provide more branches. Here you're providing four branches as well, okay? At one given section. So you can add, or increase the area that the stirrup provides, okay, by adding more and more branches. The typical thing is 2 branches, but for larger sections, you can definitely have 4 branches, either like this or like this, okay, to add to the area of the stirrups. If you're going to bake your stirrup over here, you need to have a large overlap area that is equal to 1.3 of the development length. The development length is the length required by the bar to develop the maximum tensile force that will be developed in. Okay, so you have to have this overlap over here. Okay. Also here we said the ACI code limits, the magnitude of the yield stress of the stirrups to 60 KSI. So if you're using, let's say, grade 75, so the yield stress of grade 75 is 75 KSI, you can still use it, but when you write the design equation, you're going to assume that F yield is equal to 60 KSI, not 75. The limitation for F yield for the stirrups is 60 KSI. You can use higher ones, but you're going to, in your design, you're just going to use 60 KSI, not 75. Okay? Why is that? Because as the strain in the stirrups increases, okay, the width of the crack is going to increase. We said we have this inclined crack over here, right? We have this crack, so we want to limit the width of this crack to be as small as possible. So as the strain here increases, the width of that crack is going to increase. So to limit the strain or the width of this crack, you have to limit the stress or the yield stress of the steel, okay, to just 60 KSI. Okay. Here are some benefits of using those stirrups, not only to carry the shear, but it also promotes the aggregate in the log. It confines the core of the concrete, okay, so that it increases the strain of the concrete itself in terms of bending, okay. Confines the longitudinal bars and prevent cover from breaking off the beam, and hold the pieces of the concrete on either side of the crack together and prevent the crack from propagating in the compression zone. Okay. This is the design equation we mentioned last time. So you have the shear force. Part of the shear force will be carried by the concrete, and we know how much the concrete can resist. And now for the stirrups or the bent up bars or whatever bars you're using, okay, whatever type of reinforcement you're using, how much VS, the strength that the stirrups or the steel can provide, it's VS, it's AV, the area of those stirrups, multiplied by the stress, okay, the yield stress of those stirrups at yield tension, multiplied by the number of the stirrups along the crack, okay. We said we have your crack over here. We're going to assume that the width of the crack, this is, conservative, but that's what's recommended by the ACI code. We're going to assume that the width of the crack is D, okay? So if the spacing between the bars are S, so over here the number of those stirrups crossing this crack is D over S, okay? That's the number of the stirrups crossing that crack. So this is the number here, which is D over S. So Vs, the strength provided by the stirrups, is AV F yield E divided by S. This is the ACI equation 22.510.53. Okay? You don't have to memorize it. It's in the code here. So in this equation, you have two variables, AV and S, two design variables. You can choose whatever area for the stirrups you want and the spacing. You can play with those two numbers. So let's say you just assume, you have to assume one of them. So let's say you say, okay, I'm going to use 2 branch stirrups number 3. Okay, so you know that area. It's 2 branches, the area of 2 branches, and it's number 3, so you can find the area of a number 3 bar. Okay, so you know how much is AV. So if you know the AV, now you need to find S based on the shear force applied on the section, the spacing. So the spacing comes from this equation. So S is going to be AVE. AV F yield D divided by Vs. Okay? If you have, so this is what we reached last time. So if you have inclined stirrups or bent up bars, okay, this equation remains the same except that you have to multiply by this factor, sine alpha plus cosine alpha. Okay? And this equation again is in the ACI code up to this one. Okay? So if you have inclined stirrups or bent up bars, the angle, okay, of inclination here is phi, okay, and that gives you the strength of the stirrups that you have here. Okay, so this is the angle phi over here. This is what we mentioned last time. The strength provided by the concrete plus the strength provided by the steel gives you the total strength provided by the section. But that's the nominal strength of the section, okay? The ultimate strength is just phi multiplied by this value, okay? So multiplying this equation by phi, so phi multiplied by Vn, that's V ultimate, is equal to phi Vc plus phi multiplied by Vs. So the amount of shear strength that you have to provide by the stirrups, okay, Vs is V ultimate minus phi Vc divided by phi, okay? How much is phi? It's not the value that you used to use for bending, okay? So phi for bending is different from phi for the shear. For shear, it's just 0.75, okay? It's not 0.9 or that equation that we used to use, 0.65 plus 0.25 multiplied by the strain minus 0.002. No, this is only for bending or axial stresses, okay? So phi here for shear is just 0.75. So that's the amount of shear reinforcement or shear, or this is the amount of shear strength provided by the shear reinforcement here, or required to be provided by the shear reinforcement. Okay? Any question? Okay. So when would you need then to provide shear reinforcement? We said the strength is going to be carried by the concrete and the steel, right? So typically you would think that if the shear force applied on the section is less than the strength of the concrete, then you don't need shear reinforcement, right? The applied shear force is less than the strength provided by the concrete, then you don't need shear reinforcement. The concrete alone is enough, right? That's correct, okay? But the ACI code has some requirements here, okay? So the ACI code in section 9.6.31 says that if FVU, the shear force applied on the section, exceeds 1/2 VVC, okay, even if it's less than VVC, okay, you still need to provide stirrups. Stirrups are required, okay, and there are some certain exceptions for this, okay. So you don't need shear reinforcement, but you're going to provide some stirrups because the ACI code requires you to provide those stirrups, okay? So the thing is now, if V ultimate is in between VVC and VVC divided by 2, okay? It means that you're going to have to provide some stirrups, okay? So let's write this here so that you understand this. V ultimate is the applied shear. Okay? If V ultimate is larger than VVC, then typically you need shear reinforcement. Right? The concrete is not enough. The applied shear force is larger than the strength of the section, of the strength of the concrete. So you need to provide some stirrups to resist this difference, okay? But the ACI code here says that even if it's less than VVC, if the applied shear force is less than VVC, okay, but it's larger than 1/2 VVC, okay, it's enough, the concrete is enough, but still you need to provide a minimum amount of stirrups. Okay? Typically, the last thing is if V ultimate, okay, is larger than VVC divided by 2, so no stirrups required. So here, you don't actually need to provide shear, okay? The shear is, like the concrete is enough, but you need to provide some minimum amount of stirrups, okay? Just the ACI code requires this. So how much is the minimum amount of stirrups that you can provide in a section? So this is given in section 9.6.3.3 in the ACI code, okay? It's 2 equations. So that's the minimum amount of shear reinforcement that can be provided, okay? You cannot put less than this amount. AV minimum here is 0.75 square root FC prime V web S. S is the spacing between the stirrups, okay? Divided by F yield of the stirrups in PSI. FC prime is in PSI as well. And it has to be larger than 50 V web S divided by F yield in PSI as well. So you have to write this equation and this one and use the larger value of the two equations, okay? So you're going to apply this one, you're going to get some number, you're going to apply this one, you're going to get some area for the stirrups, okay? And then you're going to use the larger value of both values, okay? So here it says there are several exceptions for this requirement, okay? That you have to provide some stirrups if V ultimate is larger than VVC divided by 2. What are those exceptions? So those exceptions are here. Footing and solid slabs. So in slabs and footings, you don't need to provide shear reinforcement if you don't need them, okay? Concrete floor joist. What is the definition of concrete floor joist? It's given in section 9.8 of the ACI code. You still don't need to provide stirrups or shear reinforcement if you don't need them. Shallow isolated beams with H larger than 10, you still don't need to provide them. Beams built integrally with slabs and H, the height of the beam, is less than 24 inches an H not greater than the larger of 2.5 times the flange thickness or 1/2 the web width. Still, you don't need to provide the minimum amount of shear reinforcement if you don't need them. Okay? Being constructed with steel fiber reinforced concrete with strength not exceeding 6 KSI, and V ultimate is less than 2 phi square root FC prime B web D. Okay? Definitely, those are in the ACI code. Okay? In section 9.631, so you don't need to memorize them, but you need to know what section they are in. Okay? Now, some other things. 9.6.31. Okay? So now, other requirement by the ACI code here. We said you have this crack, okay? And you're going to have those stirrups, you know, crossing this crack and resisting the shear force that is not resisted by the concrete. Okay? So let's say you need a spacing here that is 10 inches, 20 inches, 30 inches. Is there a limitation for this? Yes. There is a very, very important limitation for this. This spacing cannot be larger than D, right? If it's larger than D, that means that there might be some crack, okay, with a width of D, and there is no stirrup crossing that crack. So although you just need a very large spacing, but there is a limitation for that spacing that can be provided, okay? So this is what you have over here, okay? To ensure that every diagonal crack is crossed by at least one stirrup, the maximum spacing of stirrup is the smaller of D divided by 2, or 24 inches, okay? So that's the maximum spacing. It's D divided by 2, or 24 inches. This is if VC, so this requirement, D divided by 2, or 24 inches, this is if VS, okay? VS is less than 4 divided by square root FC prime B web D. If VS is larger than 4 multiplied by square root FC prime B web D, okay? So the maximum spacing, okay, is halved, okay? So it's not D divided by 2, it's D divided by 4, or 12 inches, okay? You still don't have to memorize this, but you need to know where's those requirements. It's in section 9.7.6.2.2, okay? So that's the maximum spacing of the stirrups. It cannot be D divided by 2 or 24 inches, okay? If VS is less than 4 multiplied by square root FC prime B web D. If it's larger than this value, then it's D divided by 4 or 12 inches, okay? Another requirement by the ACI code in section 22.5.1.2, okay, is that VS cannot be larger than 8 multiplied by square root FC prime B web D. If VS is larger than this amount, the shear force resisted by the stirrups cannot be larger than this amount, okay? You would say, okay, I will provide large number of stirrups. No, that's the limitation. The VS cannot be larger than this amount, okay? If it's larger, then this is not a good design according to the ACI code. So what will you do? You have to change the dimensions, increase the dimensions of your beam so that VC increases, the strength of the concrete increases, the amount of the shear resisted by the concrete increases, and the amount of shear force to be resisted by the steel reinforcement becomes less, okay? It has to be less. VS, the amount of shear force resisted by the steel, has to be less than 8 multiplied by square root FC prime B web D. It cannot be larger than this magnitude, okay? Any question? That covers the requirements regarding the equations, okay, to be used in the design for shear, okay? We're going to summarize those so that you don't get lost, okay? But those are all the requirements given by the ACI code regarding the design of shear reinforcement, okay? So but there are some requirements, okay? Not as equations now, but, for those, stirrups, okay? For those stirrups, okay, you need to provide hooks at the end of the stirrup so that they can provide, the tensile force in them, okay? Those are given the dimensions or the requirements for those hooks are given in section 25.7.1, okay? So here, if you have those stirrups, you need to have a hook here, okay? A hook here, so that it provides the tensile stress. It will be able to provide the tensile stress over here, right in the middle of the stirrup, okay? So the requirements for those hooks here, this hook has to be 6 multiplied by the diameter of the bar, the longitudinal bar, okay? If you have a 90 degree, this is a 90 degree hook, 90 degree hook for number 5 for smaller stirrups, okay? Also you can use this length, 6 dB, for number 6 and number 7 and number 8 if the stirrups if F yield is less than 40,000 psi. If it's more than F yield is more than 40,000 psi, then the length of the hook here has to be 12 multiplied by the diameter of the bar. Okay? Or you can use, instead of 90 degree hook, you can use a 135 degree hook or a 180 degree hook. Goes like this. Okay? In this case, this length is just 6 dB, but not less than 2.5 inches. Okay? So that's the length of the hook required for those stirrups. Okay, you can either use 90 degree hook or 135 degree or 180 degree. Okay? If you use 135 or 180 degree hook, so the length of the hook over here has to be 6 dB and not less than 2.5. If it's 90 degree hook, then it's 6 dB if it's number 5 or less, or 12 if it's numbers 6 or 7 or 8. Okay? It has to be 12 dB. This is if F yield is larger than 40 ksi. Okay? Usually we have grade 60. Okay, the grade 60 is the most popular case, so definitely it's going to be this case, 12 dB if you have the stirrups being larger than number 6 bars. Okay? Okay, so now when you design your beam, let's go here, let's draw this. You have a beam that looks like this. Let's say with some uniform load, the easiest case. You want to design this beam for shear. You need to find the stirrups required to resist the given shear. How to calculate the given shear? You have to design it for the maximum shear on this beam, right? The shear is not constant. So what do you need to do here? Draw the shear force diagram, right? So how does the shear force diagram look like? How does the shear force diagram look like?
Triangle all the way up to the middle.
Right? This is what you mean? So when you design this beam for shear, where's the magnitude of the shear that you have to design it for? At the end here. So this is V ultimate, right? Maximum. It occurs at the support. So you have to find this value and then you design your beam based on this value, right? Okay. The ACI code permits, allows you, okay, that you would design it for smaller value. How much is that smaller value and why? Okay, would you design it for a smaller value for the shear? Okay, let's see how much is that value and we're going to explain why. It allows you to move a distance d from the support. So you move here a distance d from the support, okay? As you move a distance d from the support, the shear will decrease a little bit. It's not this value, it decreased some you know, by some value, this part, right? And you can design it based on this value. You just go by distance d from the support. Okay?
Dr. Grubb,
Yes.
why is that? Because when I was doing the FE review,
Yeah.
we had a question like where would the shear be the max, and I chose at the end,
Yes.
but the answer was like
At
it was
distance
like
d.
yeah at like a distance d from.
Okay. We're gonna. Actually, the when you draw this is the maximum shear force. It's over here, but actually this is not applied. It's going to be applied on the beam. Okay. Let's see why. Why the ACI allows you to move a distance d from the support. Actually, your beam doesn't look like this. Okay. It's not a line, and the support is not that, you know, thing that we draw, right? The beam looks like this. It has a section, and the support is a column, right? Like this.
Is it a distance d with the column?
So D is the depth of the beam, right? That's D. So the load, you have a uniform load applied here. Right? So actually what would happen when you have a load like this, okay? This, you know, by experiment, okay? If you draw a line with a 45 degree here, this is 45 degrees, okay? This load, this part of the load, will just go to the column right away, okay? It will not cause shear here, okay? So this load just travels to the column right away without providing any shear, okay, in the beam. So that's why if this is 45 degrees, this is D, so this width is D. So you actually have to calculate the shear here at a distance D. This is similar to what? If I draw a beam to you like this, and I give you a load here, P, would that P over the column, over the support, give any shear in the beam? No, it would just travel to the support right away, right? So that's what happened here. Any load within this distance D, okay, will just travel to the support without providing or, you know, resulting in any shear in the beam itself, okay? So the ACI code allows you to design the beam on the shear force based at a distance D from the support. Okay? That's why. Okay? Is it clear now? Okay? But there are exceptions for this, you know, allowance. Okay? What are those exceptions? Let's see, the exceptions here. Now you understand what we did here, okay? You understand this load will just go here right away, right? Let's say your beam looks like this. This is your beam, and this is the column here. Okay? What's this? If you take a section, so actually your beam looks like this. A reinforced concrete beam that looks like an I-beam, okay? And still, it's concrete, okay? It's not steel, okay? So this section, you have some steel here, it's reinforced concrete, okay? And the load is applied here. On the lower flange. Would you use this, you know, you would decrease your V ultimate, you calculate it at the distance D? No, because this here, this load, to go here, you don't have a distance D, right? If you had a distance D, the depth of the beam, if the load was on the upper flange, on the top of the beam. But if the load is applied on the lower part of the beam, you cannot decrease the magnitude of the shear. You have to use the shear at the support, okay? Not the shear at a distance D from the support. So that's one exception, okay? If the load is applied on the lower part of the beam, you cannot decrease your shear, okay? Another exception is when you have a, something like this also. So actually the column is, or the part that is supporting your beam is on the top, okay, on the lower part, and the load is on the top. So if this part, at the distance d, no, it will still cause shear. Even the load till this point will still cause shear to your beam, okay? So this is another exception. So those are the cases where there is no reduction permitted, okay? So this case where the load is on the lower flange, and the last case here, okay, when you have a corbel, okay? For a corbel, even if the depth of this corbel is d, okay, and this width is less than d, you have to design it for shear here, okay, for the shear at the face of the corbel, okay. And if you have a concentrated force, okay, that is closer or within the distance d, so again here the ACI code says you have to take this concentrated force into account as part of the shear, okay? You cannot neglect it. Okay? So when you design your shear for shear, you just go a distance d from the support, okay, and you design your beam based on that magnitude of the shear, not at the support itself. You just decrease it by a little bit, okay? What if you don't decrease it? Yeah, just waste of money. It's not a wrong design, but you're going to design it to resist more shear than required, okay? So it's not a bad design. It's not a fatal mistake, okay? It's actually more, safe, but why have it more safe than required, okay? And pay for that. So here, this part, I don't know if we're going to solve an example. We have an example on this, but anyway, when you design for the shear, okay, at the midsection, when you have a beam like this, okay, and you want to find the shear right in the middle, how much is the shear right in the middle of the beam?
Depends on the load.
Okay, so it depends on the load.
0?
It's 0 if you have a uniform load that is applied over the entire length of the beam, right? So usually if you have a dead load and a live load, okay, where will you know the location of the load?
Dead load.
Hmm?
The dead load's always going to be.
The dead load is always going to be over the entire length of the beam, right? That's the dead load, right? Because the dead load comes from the weight of the beam or even from the slab that is on top of the beam, so it's everywhere, right? And you cannot change this. So if you have a load that looks like this, how much is the shear in the middle?
0.
0. Okay. What about the live load? You don't know, right? The location of the live load. So if you don't know, why you don't know the location of the live load? Because it can change, right? So you want to maximize the shear right in the middle. How to maximize the shear in the middle due to the live load? We did this in structures 1. Influence lines, okay? So you have to draw the influence line, okay? So you draw the influence line for the shear right in the middle, okay? To find, okay, how much or where to put the live load. So you're actually going to find that you need to put the live load here, so that the shear in the midsection is maximized. You have to draw the influence line for the shear. Let's say this is point C. You have to draw the influence line for the shear at point C. Okay? So to draw the influence line for the shear at point C, it would be, let's say, see here, it's going to look something like this. So if you have a load here, it's going to give you a negative shear. If you have a load here, you're going to have a negative shear. If you apply the load over the entire beam, then the negative shear is going to cancel the positive shear, so you're going to have zero shear if you have the load over the entire beam. But to maximize it, you just put the shear, or the load here, so that the shear here is maximized. It's the maximum positive shear. Okay? Any question? Okay, so now for the summary, okay, for the design. This table is very, very, very nice. It summarizes the design process for shear reinforcement, okay? First, you draw the shear force diagram. To design the beam, you need to know how much is the shear force that you should design your beam to support, okay? You draw the shear force diagram, and then you calculate V ultimate at a distance D from the support, and take care of those exceptions, okay? You find this shear force, the maximum shear force, and then you go a distance D from the support to find this shear force. And then you need to see how much the concrete can provide as strength to resist the shear force, okay? So how much can the concrete resist? It's PVC, okay? Phi multiplied by VC, which is that equation in the ACI code 22.5.51. It's 2 lambda square root FC prime B web D. Okay? So that's VVC. If the V, the shear force applied on the beam at the distance D, is larger than 1/2 VVC, okay? With those exceptions that we mentioned, okay? Then you need to have stirrups, okay? If it's less, then you don't need to have stirrups, and that's your design. What's the design? You don't provide stirrups. The dimensions of the beam, the V web, the width and the depth of the beam that is given, okay, is good, okay? To resist the shear alone without providing any stirrups, okay? So, but what if V ultimate is larger than this amount, okay? You need to find the spacing of the stirrups. So how much is the spacing of the stirrups? It's given from this equation. If you use vertical stirrups, then it's AV FU B divided by VS. Okay? That's the equation that we mentioned, okay? The required stirrups, spacing for the stirrups. How much is VS? VS is V ultimate minus VVC divided by phi. The difference between the applied shear force and the amount of the shear force provided by the concrete. Okay? This is what has to be resisted by the shear reinforcement. Okay? Now, once you find this S, this spacing for the stirrups, you have first to find this S in this equation, you have to assume the AV. How much is AV? The area of the stirrups. It's the area of the stirrups of the stirrups that you have. Let's say you assume you're going to use number 3 or number 4. Usually for stirrups we use number 3 or number 4, not more than this, okay? And the number of branches that you have, maybe 2 branches, 4 branches. The usual thing is 2 branches, just 2 branches, okay? And then this spacing, you have to make sure that it's compliant with the requirements of the ACI code. So what are the requirements for this spacing, okay? S minimum, okay, it cannot, or yeah, S maximum, okay, it cannot be larger than this amount or this amount, okay? This is equation 9.6.3.3, okay? And S maximum cannot be larger than D divided by 2 or 24 inches if VS is less than 4 multiplied by square root FC prime B web D, or it cannot be larger than half of this value, which is D over 4 or 12 inches if VS is larger than 4 multiplied by square root FC prime B web D. Those are in section 9.7.6.2.2. Okay? And VS, you also, once you calculate VS over here, you have to make sure that it's not larger than 8 multiplied by square root FC prime B web D. If it's larger, then you have to change the dimensions of the beam. Okay? Any question here? Okay, great. So we have some examples here, but since I kept you, you know, for a longer time last time, so we're going to stop here. Any question? Okay, let me see how many students do we have here. 3, 4, 5, 6, 7, 8, 9, 10. Okay, so only maybe one student is missing. So again, for those who wasn't here, okay, when we started the lecture, I won't be here on Monday, November 12th, and Wednesday, November 14th. Okay, so we're gonna have our midterm exam, the second midterm exam, on one of those 2 dates. Which one do you prefer? 14. Okay, so let's, who wants 14? Just raise your hand. Okay, so it's 14, okay? I'm just gonna send an email that's gonna be on Wednesday, November 14th.